So in this topic, I'm going to introduce you to a component called capacitors, and capacitors have the ability to store charge. So if these are connected up to a battery, they can then accumulate charge on them, and they can then release that charge in a later scenario. And now capacitance is a property of these so-called capacitors. And what it is the charge stored on the capacitor per unit volt. So our capacitance, which is denoted by the letter C, is therefore given by the equation Q, which is your charge, over V, which is the voltage applied across it. So your capacitance equation is more commonly known as Q is equal to CV, where Q is your charge in coulombs, V is the voltage applied across the capacitor in volts, and C is your capacitance, and it can have unit of clearly coulombs per volt, but more commonly it is known as farads, denoted by this F here. So let's say we have a generic capacitor and we vary the voltage applied across it and measure the charge accumulated on that capacitor. What you'll see is a graph that looks something like this. And we know it's a straight line due to the equation Q is equal to CV, and it therefore has constant gradient of the capacitance value. Now the energy stored on this capacitor is given by the area under this graph. And you can see that this is clearly a triangle, so the energy stored is equal to a half times the voltage applied across the capacitor times the charge stored on it. So this is the equation for the energy stored on a capacitor. And because we know that Q is equal to CV, we can also get variations on this equation such as E is equal to a half CV squared, or E equals a half Q squared over C. So we've looked at how we can calculate the energy stored on a capacitor. Now let's look at some of the factors affecting the capacitance of that capacitor. Now we'll go over this in a bit more detail in a later video, but a capacitor is simply two metal plates with positive charge stored on one plate and negative charge stored on the other. And because you have a very positive plate here and a very negative plate here, what you can see is sparks can sometimes fly between the plates. And this is obviously due to a transfer of charge or electrons. So one way in order to prevent this is by simply adding something called a dielectric, which is simply a piece of material that stops these charges from being exchanged. So by adding a dielectric, you inherently increase the capacitance of this capacitor. And some of the other ways that you can change or increase the capacitance depends on the surface area of the metal plates and the separation between the plates. Well, if you have bigger surface area, you can obviously store more electrons and therefore have a greater charge. So therefore, for the same voltage, you can store greater charge, so the capacitance is bigger. So therefore, more surface area means greater capacitance. Now we'll look at this in a later video, but having lower separation between plates means that you can more easily charge the capacitor at a lower voltage. So therefore, if you decrease the separation, you can increase the capacitance as well. So the capacitance of a capacitor that you build is therefore given by the equation C is equal to epsilon naught epsilon r A over D. Now this may look confusing, but C, as you know, is your capacitance, and that's given in farads. We already looked at the surface area, which is in meters squared, and how the separation between the plates affects the capacitance, and this is given in meters. Now this epsilon naught is simply just a constant, and it's called the permittivity of free space. And you can find this in your data sheets or on your calculator. And epsilon r is simply the relative permittivity of the dielectric if you have one. And if you don't have a dielectric, this epsilon r value will have a value of 1. So epsilon r is equal to 1 for no dielectric. Epsilon r is simply just a ratio of the permittivity of the dielectric when compared to free space. So it's likely to have a number ranging from like 1 to 10 or something. Now we're going to further discuss how to charge and discharge capacitors and what they're used for. So if you find anything a bit confusing in this video, please go ahead and watch the next videos on capacitors. Now, the best piece of advice I can give you after watching that video is to go off and practice some past papers or topic questions. These are single-handedly the best way to help you commit the content you've learned to memory. Obviously, go and do all the YouTube stuff of liking, subscribing, and if you found this video helpful, feel free to go and watch any of my other ones.